Hi everyone, my name is Trinity, and today we're going to be going over Z effective. So in this video, we're going to go over question 1 in your pre-workshop, and for now let's just focus on part A, which asks us to complete the following table on the left side of the screen. So to fill out this table, we're going to need to draw a board diagram for each element, and in order to fill out the board diagram, we're going to need a periodic table. So let's start with lithium. So from the periodic table, we can see that lithium has an electron configuration of 1s2, 2s1. And we can use this electron configuration to fill out our board diagram. So we can see that there are 2 electrons in the first shell and 1 electron in the second shell. And we know that there are 3 protons in the nucleus from the periodic table. Once we've filled out the board diagram, the next thing to do is locate the external charge, which is just the outermost electron, which in this case would be this electron. Once you've located the external charge, then you can calculate Z effective. So if you remember, Z effective stands for the effective nuclear charge, and the effective nuclear charge is equal to the charge of the nucleus plus any additional charges. So to find the charge of the nucleus, you just count the number of protons, because protons are the only charged particle in the nucleus. So lithium has 3 protons, so the charge of the nucleus is positive 3. Now we have to deal with the additional charges. And to find the additional charges, you just have to look at all of the electrons besides the external charge. So that means, in lithium's case, that would be this electron and this electron. So these electrons are in the first shell, and our external charge is in the second shell. If you remember from Gauss's law, charges that are closer to the nucleus than the external charge can be treated like they're in the nucleus. So we can treat these 2 electrons like they're in the nucleus, and since each electron has a -1 charge, we are adding a -2 charge to the nucleus. Because once we've accounted for all of the electrons, then we can calculate Z effective, which in this case would be 1. So now let's calculate Z effective for beryllium, which has a electron configuration of 1s2, 2s2. So we're adding another electron into our second shell, and we're also adding another proton because beryllium has 4 protons. So now we have to find our external charge, but this time we have 2 electrons in the outermost shell. Since these electrons are basically identical, it doesn't matter which one we pick as our external charge. I'm just going to keep the highlighted one as our external charge. And I'm going to call the external charge A, and I'm going to call the other electron B. And that'll be helpful later. So now let's calculate Z effective. Once again, the charge of the nucleus is just the number of protons, so it's +4. And now we have to deal with our additional charges. So, according to Gauss's law, the 2 electrons in the first shell can just be added to the nucleus because they're closer than the external charge. So we're adding a -2 charge there. Now we have to deal with electron B. So electron B and electron A are in the same shell, which means they're basically identical. And if they're basically identical, then there's a 50-50 chance that one of them is closer to the nucleus at any point in time. So we can treat this like half of B is closer than A and half of B is farther from the nucleus than A. And according to Gauss's law, we can treat the half of B that's closer than A like it's in the nucleus. So that means we are adding half of a negative charge to the nucleus. And the half of B that's farther from the nucleus than A can be ignored because Gauss's law says that charges farther away from the nucleus than the external charge can be ignored. Now that we've calculated for all of the electrons, we can calculate Z effective, which would be 1.5. So now let's calculate Z effective for boron. So boron has an electron configuration of 1s2, 2s2, 2p1. And I know 2s and 2p aren't exactly the same, and the 2 orbitals have slightly different shapes, but in this question, we can put 2s and 2p electrons both in the second shell. So we're adding another electron to the second shell, which I'll call C, and we're adding another proton to the nucleus, because boron has 5 protons. So the charge of the nucleus is plus 5 from the protons. And now we have to deal with our additional charges. Once again, the electrons in the first shell can be moved to the nucleus, so that provides a -2 charge. A and B are identical, so half of B is closer than A and half of B is farther than A, so the half of B that's closer contributes a -1/2 charge. A and C are also identical, so half of C is closer to the nucleus than A and half of C is farther away, and the half of C that's closer contributes another -1/2 charge. So taken all together, the Z effective for boron is 2. So from here, you should be able to see a pattern. You should notice that all of the electrons in a shell closer to the nucleus than the external charge contribute a full negative charge. And you should notice that each electron in the same shell as our external charge contribute half of a negative charge. So let's take that into account when we do our next element. So now let's do carbon, which has an electron configuration of 1s2, 2s2, 2p2. So we're adding another electron to the second shell, and we're adding another proton. And let's calculate Z effective. The charge of the nucleus is +6. Now we have to deal with our additional charges. So the electrons in the first shell contribute a full negative charge, and we have 3 electrons in the outer shell, excluding our external charge, and each of them contribute a -1/2 charge. And that means our final Z effective will be 2.5. Now we can do nitrogen, which has an electron configuration of 1s2, 2s2, 2p3. We're adding another electron to the second shell and 1 more proton. So our charge of the nucleus is 7 from the protons. And now we have to deal with our additional charges. So the electrons in the first shell contribute a full negative charge. And we have 4 electrons in the outer shell, excluding our external charge. And each of those contribute half a negative charge. And our final Z effective would be 3. So by now you should notice that the Z effective is going up by half for each element, and there's a reason for that. Each time we go, for each element, we are adding a full proton to the nucleus, and that proton contributes a full positive charge to the nucleus. And we're adding another electron to the outermost shell. And we've established that electrons in the outermost shell, along with our external charge, only contribute half a negative charge. So if we're adding a full charge and subtracting half a charge every time we go up an element, then the net change for each element is +1/2, which is why each element increases by half in the table. So that means oxygen is 3.5, fluorine is 4, and neon would be 4.5. So we've completed the table to the left, but I want to make it clear that this is an approximation because we are kind of approximating the shielding effect for the electrons. The actual Z effective, if you get the shielding perfectly right, looks like this. Oops. Okay. So now we're done with part A. And we can do, And we can do part B. And part B asks us to write an equation relating Z effective to Z and S, which represents the number of electrons shielding the electron of interest. So we know that the effective nuclear charge is Z effective. And we know that the charge of the nucleus is just equal to the number of protons, which is Z. And we've been calculating our additional charges by looking at all of the electrons besides our electron of interest, aka the external charge, which tells us it's S. But since electrons are negative, it is -S instead of +S. So this is our answer to part B. Thank you for watching.